The Indian Association of Structural Engineers, also known as IS-Struct-E, was conceptualized and constituted in the year 2002 by a group of senior professional structural engineers from all over the country. IS-Struct-E is registered under the Societies Registration Act 21 of 1860. IS-Struct-E is a national apex body of structural engineers in India with a mission to promote structural engineering profession and cater to the professional needs of the structural engineering fraternity. In the short span of 2 decades, association has attained an eminent position in the professional field. Its membership is valued very highly in the profession. Since inception, IS-Struct-E has been led by eminent structural engineers like late Shri Mahendra Raj, late Shri Shri Kumar Ghosh, late Shri Subhash Chand Mehrotra, Professor Mahesh Tandon, Shri Manoj Mittal, Professor R. Pradeep Kumar, and Shri Alok Bhaumik as its president. IS-Struct-E is a permanent member of Engineering Council of India and interacts with the government on professional and policy matters related to civil and structural engineers. To expand its reach, IS-Struct-E has collaboration with various international professional like-minded associations and institutions like IS-Struct-E, UK and FIB for strengthening global connections and professional exchange. IS-Struct-E's prime objective is supporting and protecting the profession of structural engineering by upholding professional standards and acting as a mouthpiece for structural engineers in India. IS-Struct-E endeavor to ensure that its members develop the necessary skill in structural engineering and work to the highest standards by maintaining a commitment to professional ethics and standards. IS-Struct-E is actively engaged in organizing several continuing professional development CPD courses for structural engineers to help them update their knowledge and advance their career paths. It also conducts refresher courses for young and practicing engineers and student-oriented programs. Seminars, workshops, conferences, technical lectures and discussions related to the latest technological advancements and case studies are also organized regularly for members to enable them to continuously update their knowledge and skill set by interacting with the best minds from the industry. IS-Struct-E's activities are widely appreciated and known for quality technical contents. IS-Struct-E is also actively engaged in publishing its quarterly journal Structural Engineering Digest SED, code commentaries, professional guidelines, monthly newsletter, and Crossfall, a unique quarterly newsletter that confidentially reports structural failures and the lessons learned from them. IS-Struct-E's publications are becoming popular with time. IS-Struct-E has representation in various technical committees of BIS and IRC as well. Its members are actively contributing to National Code of Formulations. In the year 2020, IS-Struct-E started National Awards competition to stimulate interest in the structural engineering field and to promote innovative thinking and creativity. The awards are presented to the winners in recognition of their outstanding contribution to structural engineering in the categories which include Outstanding Structure, Outstanding Structural Engineer, Outstanding Woman Structural Engineer, Promising Young Structural Engineer, and Best Master's Thesis in Structural Engineering. Reaffirming its commitment to professional excellence, IS-Struct-E launched the accreditation program in 2023. This flagship initiative empowers practicing engineers to evaluate their competencies, identify growth opportunities, and strengthen the foundation for sustained professional success. IS-Struct-E is currently operating from 4 regional centers, namely Eastern, Western, Northern, and Southern, having its headquarters in Delhi to inculcate the professional culture and provide handholding to the budding engineers. Joining IS-Struct-E offers exclusive resources, mentorship, and networking with industry leaders. Members enjoy discounted registration for workshops, seminars, and events, along with discounted membership of FIB, opportunities for certification, career guidance, leadership roles, and enhanced professional recognition. IE Struct E has its student chapters in several leading engineering institutions as well. Membership of IE Struct E is open to all civil and structural engineers engaged in structural engineering profession. Members are elected based on their qualifications and experience in different grades as per eligibility requirements prescribed in the bylaws. Each application is carefully scrutinized before electing the members. More information about IA Struct E is available on its website www.iastruct.co.in.
Hello.
Yes, sir. Please start, sir.
Shall I continue?
Yes, sir. Yes.
Dear friends, I wish all of you a very happy new year. In the monthly webinar series, today's webinar is on the application of spectral finite element method for nonlinear analysis of concrete gravity dam. We welcome Professor Ashutosh Bagchi, who is now a leading professor and consultant working in Canada. And early morning, he will be sharing on the about topic. About Dr. Ashutosh Ghosh, he graduated from Jadavpur University and there worked for some time in the industry. Further did his MTech in structural engineering from IIT Chennai, Madras. And further he went to Canada, where he did his PhD in structural engineering from a reputed university under a well-renowned person whom I also know personally, Professor G.L. Humer. Dr. Bagchi is a professor now of structures and infrastructure engineering of Concordia University, Montreal, Canada. He served as a departmental chair from 2017 to 2023, and also he is a licensed professional engineer. He is a fellow of the Canadian Society for Civil Engineers. He is internationally known for his research in structural health monitoring, earthquake engineering, and smart infrastructure with over 200 publications, and obtained Teaching Excellence Award. About the topic, he shall be presenting on the above subject, and his presentation provides an introduction to the spectral finite element method and the development of a novel 2D time domain plane spectral finite element with material nonlinearity. The performance of the element is demonstrated through a set of benchmark problems and applied to nonlinear seismic time history analysis of a concrete gravity dam. Now I request Professor Bagchi to proceed. Professor Bagchi, please continue.
Thank you, Professor Dhawan. Thank you for the kind introduction. So I will share my screen. So is it visible?
Yes, sir.
Yes.
Okay.
Yes, sir. Make it in full. The presentation.
Yeah, let me put it in slideshow mode.
All right.
Is the slideshow visible?
Yes, sir.
Yes.
Okay, good. All right, thank you everyone. Good evening there. And it's morning here, and it's a cold, snowy day. Although it is not snowing right now, but it's covered with snow. So the topic of presentation here is application of spectral finite element method for nonlinear analysis of concrete gravity dam. So what I will do is I'll give you an introduction of the method, describe what is spectral finite element method, go over a few benchmark problems, not necessarily in dams, in everything else, and then we'll go into a case study with dams, including the nonlinear effect of AAR, which is called alkali aggregate reaction that is common in some concrete. So finite element method, we all know what it is and how it works. It is highly popular numerical method for structural engineers. We use finite element method for analyzing structures for everything. One of the major thing in finite element analysis is modeling the structure appropriately, meshing it, choosing the appropriate elements, loads, the boundary conditions, etc. And computational aspect is also important, because if our mesh is too dense, then the analysis takes too long, and verifying the results also becomes a challenge. So the new set of methods that were developed, I wouldn't say it is new anymore, but it is still developing, so that the newness or novelness still exists, is called spectral finite element method. Spectral meaning is that spectral sometimes mean range or range of frequencies for which it will work. So I'll explain what it means as we go. So here the general objective is to develop the alternate computationally efficient method, demonstrate how the time domain spectral finite element works, and demonstrate its applicability in structures like deep beams, dams, etc. Because this is developed for 2D, means we are applying it for plane stress, plane strain condition. And I will also explain a new way to look into alkali aggregate reaction in concrete and how to model it numerically. So spectral finite element method, as I said, that spectrum means range of frequencies. So if we can envision a structure where we can approximate its geometry with a range of Fourier components, then use those components for the analysis. And this is a very old technique. It is not a new technique in expressing a geometric form in Fourier series. But what is novel here is that applying it in the context of finite element, so that we reduce the number of elements. But for irregular geometry, it doesn't work very well. So that's why there was a development in going with the traditional finite element route, but changing the shape functions, changing the way the integration is done to make it more efficient. So we call it TDS-FEM, or time domain based spectral finite element method. Okay. So frequency domain based method, which is the original spectral method, which has a lot of advantage because it reduces the number of element and improves the computational efficiency, but it is not always convenient for irregular geometry. So that is the disadvantage that is outlined here. So I will move further to this. So for time domain method, it is very similar to p-type finite element. P-type means that the number of elements may remain same, but the order may be increased. The order of polynomials and integration. And also, instead of Gauss quadrature method for numerical integration, we use Gauss Legendre Lobato quadrature method, which is slightly different and more efficient. And this causes the mass matrix to be diagonal, and it leads to reduction of computation method compared to the finite element method. So if we use regular finite element method, automatically the mass matrix becomes, if we use consistent mass matrix, it becomes non-diagonal. It has a band. But with GLL, it becomes a diagonal matrix. So the methodology will include how we formulate the TDS-FEM, types of analysis performed, and will present how the methodology step-by-step works. The basic essence is captured in this slide. I don't want to put too much mathematics in this presentation, but broadly speaking, the regular finite element, which is mapped as isoparametric element, where the coordinates are -1, 1, 1, 1. So it is 2 by 2 rectangle as we use in basic isoparametric element. But the mapping is done with integration with GLL, where we can do a direct integration rather than doing numerical integration as in Gauss quadrature. So types of analysis performed here is static, dynamic, linear static analysis, nonlinear static analysis, modal analysis, linear dynamic, and linear non-dynamic, nonlinear dynamic analysis. So this is the general workflow here. So we define the 2D geometry like regular finite element. And we can divide in different zones, mesh them, define shape functions, and then do the numerical integration. We compared with different numerical integration, including traditional Gauss quadrature and the GLL quadrature, and then carry out the analysis for different aspects like linear, nonlinear, static, dynamic, etc. So if we look at the context of dam, concrete gravity dam, the dam is if you consider its geometry, it may be a simple structure, but if you look at its behavior, it may be quite complex. So many a times you will see in the literature that dam is fixed at the bottom and it is standing out, subjected to hydrostatic pressure at the reservoir side. And then if it is analysis is done dynamically, mostly linear analysis is done. That is not adequate all the time. We need to consider the effect of fluid. We need to consider the effect of foundation. And also we have to consider the effect of nonlinearity in the materials in the dam. So modeling the reservoir side is here. So reservoir will be on this side, full of water. There will be some tailwater here, but primarily the pressure will come from the fluid here in the form of hydrostatic pressure as well as hydrodynamic pressure, if we are looking at the dynamic analysis. And then there will be foundation here foundation is normally modeled with the elements, finite elements here. The boundary is cut at a certain distance. But then what happens if we do dynamic analysis with this kind of truncated boundary, then the seismic waves reflects from this boundary, and then it alters the results, which is not realistic. So that's why there is the process where these are special elements are used around the boundary called infinite element, which deals with this wave reflection problem. So in spectral finite element also we need to take care of that. And the hydrodynamic force sometimes is simplified by something called Westergaard formula, where the equivalent mass is calculated for the fluid and applied here so that the inertia effect of the mass can be considered. That is okay sometimes, but the results are not always accurate. So sometimes we need to model these fluid elements as through its pressure distribution according to the fluid dynamics law. We call it acoustic elements. Okay, that gives better results. So here most of the analysis is done using added mass simplification. And for material nonlinearity, of course, we know with the famous Hooke's law, where the material remains linear until it yields. Until it yields in terms of, say, if we look at a steel bar, if we keep stretching it, at one point it will yield and linearity will be lost. So concrete, we don't have a pronounced yield point, but we can simplify it as bilinear, linear, nonlinear component where we can identify some kind of a yield. Okay. So the nonlinearity is expressed in terms of two linear segments. One is pre-yield, another is post-yield. And obviously, the kind of analysis material model we use in the finite element in linear analysis, that will not hold, because the constitutive relationship then will have to be updated after the yield every time step. Okay, and that is done through this combination of elastic strain plus plastic strain that we have to calculate on the go. And this plastic strain will depend on the amount of deformation in the element at that time of analysis. Okay. And based on that, we calculate something called restoring force. That means based on whatever strain is inflicted on each element, we back calculated how much is the force associated with that. It is not simply multiplication of the linear constitutive matrix. It has to be done on a step-by-step process. And another interesting thing we did is simulation of alkali aggregate reaction. So what happens, I'll give you a brief background of what is alkali aggregate reaction. You know, we all do concrete mix design. So we have certain portion of coarse aggregate, certain portion of fine aggregate, cement, etc., to achieve a certain level of strength. Now, some of the structures were constructed like that. At that time, it was not known that the aggregates will react with the concrete environment in the long run. So when it reacted, it formed some kind of chemicals which expanded the concrete. It's much like rusting in steel. So you can say it is internal changes, chemical changes in the concrete that increases the volume of concrete. And now if you look at a confined concrete or mass concrete, if there is a volumetric expansion, what it will do, it will maybe visually, if I can explain. So this is our dam. I have my screen is locked. I'll have to restart this PowerPoint. Just give me a second. Sorry about that. Just bear with me for a few minutes. I'm restarting the presentation.
Please.
Okay, I'll reshare. Okay, you can see the screen now. Let's go back to the place.
Yes.
Yeah, we were here. So as I was saying that suppose you have mass concrete, let's say dam. Let's consider it fixed for the time being. Say if there is volumetric expansion of this part of the concrete because of alkali aggregate reaction. So what it will do, it will try to expand and it will put all the concrete around it in tension or compression depending on the location. So if this pushes, this area will try to burst out, right? So that creates unnecessary extra stress, which it was not designed for. And there has been a lot of research, but mostly from the chemical aspects of this, how the AR happens, what kind of changes happens inside the concrete, etc. We tried to model it for mechanical analysis. Means what is how we calculate the stresses, strains, deflection because of the effect of the AR. So what we did is that we know that if there is a temperature rise in a structural element, what happens? That will create, say, suppose I increase the temperature in that area. That will also create expansion. And that expansion will create stress. We call it thermal stress within the body. So our thinking was there is that if we can simulate the volumetric expansion of concrete due to AR through thermal expansion, okay, fake thermal expansion, just for simulation purpose, okay, and then calculate the stresses and strain. But then the challenge would be to find out what should be the temperature that we should apply it to cause same amount of thermal expansion. So there are a lot of research on this, what they do in terms of volumetric expansion for AR. So we took those research and tried to use them to estimate what should be the temperature distribution that will cause that kind of expansion. And then we have to, it may also undergo regular thermal changes because of sunlight, extreme heat, etc. So we combined with that and did the analysis in these steps, okay? So with the regular temperature, pseudo temperature calculated for the AR and the all other loads like hydrostatic, etc., and did the analysis for static as well as dynamic analysis. So we have three problems we used for validation of the formulation for our spectral finite element method. Modal analysis of simply supported beam, modal analysis of a concrete gravity dam, and nonlinear static analysis of concrete deep beams. This is a beam taken from the literature. It is modeled as plane stress elements, rectangular plane stress elements simply supported on both sides, and central load is applied. So regular FEM versus SFEM, there is some differences with the regular FEM. I will explain why that difference comes in. And but our results matches with the literature results shown in 2012 work. So then we took the example of a beam. This is also taken, dam. It is taken from literature again. We compared the modal analysis results, which match quite reasonably. Then we have taken a deep beam, set of deep beams, which we tested in our lab for a different purpose, but we took these results and did the analysis with spectral finite element method. These are different specimen description, different length, depth, etc. And they are all reinforced with fiber reinforced polymer bar instead of steel bars. Like normally we have concrete with steel reinforcement, but steel corrodes in time. So that's why in Canada, they have been using FRP bars for some time, not in wide range, but in some case-specific applications. So we tried to find out the behavior of the concrete deep beams with FRP bars. So this is a typical meshing scheme. And we found out that we could trace the experimental load deflection curve with the spectral finite element nonlinear static analysis quite close. Then we took a dam. This is a dam again taken from literature. The dimensions are given here. The material properties are here. These are different geometric details and meshing. So we tried out different types of meshing, the coarse mesh, intermediate mesh, and finer mesh. And these are some of the mode shapes. And the modal analysis comparison is shown here. Now we can see that FEM and SFEM, there is some differences, but the differences keep on changing in percentage terms. You see, fast mode frequency is about 5% when we use 45 elements. When we use 405 elements, it reduces to 1%, 1.2%. And if we increase the number of elements to 1,000, it reduces to 0.21%. So this is not an unexpected thing. As we increase the number of elements, accuracy increases both in finite element and SFEM both. Okay, that's why they become closer and closer. But what is interesting to note here is that the time of computation. See, FEM takes 79 seconds for coarse elements or coarse mesh. At that time, SFEM takes 50 seconds. When you go to the highest number of elements, 1125, we see that time of computation by FEM is 2498, while SFEM is almost 60% of that. So SFEM converges little slower than the regular finite element because of the simplification made in terms of the integration. Okay, so if you see that the lower line here, as we increase the number of elements, the lower line is FEM, which converges to certain value, while the dark line represents the SFEM, which converges, which initially has a higher error, but sharply reduces and finally converges. Time taken, as I said, consistently SFEM takes lower time than the finite element method. So for time history analysis, a set of ground motion was taken from the site of the dam that we are looking at. And Rayleigh damping was considered, critical damping ratio 3%. And if we look at the displacement time history at the crest, SFEM and FEM, both produce comparable results in terms of much lower computation time. So if we consider the effect of reservoir, the results are also comparable. This is the principal stress distribution within the dam body. The maximum principal stress, as you see, the stress is higher here and higher here, which is expected. So one of the failure modes in this kind of dams, if the earthquake is very strong, that there is a crack along this neck, or there will be some kind of damage in the heel. So the stress distribution indicates that. And this is the minimum principal stress, which is basically compression. Again, in these areas is low, and the other areas are moderate. Then we can use this method also for damage localization. If we say hypothetically, if we have some information about the dam's behavior in real time, say there are some instrumentation in the dam and there was an earthquake, then the instrumentation will pick up the pattern of behavior in the structure. So previous to earthquake and after the earthquake, if we compare the instrumentation data, we can try to find out its changes in behavior in terms of displacement, in terms of strain, in terms of frequencies, etc. Then using those modal shape frequencies, technically, we can try to find out what kind of damage the structure might have had. So these are the plots of something called damage index based on modal shapes. Okay, because mode shape will change. And if we calculate the curvature of the mode shapes and compare them and plot them, they can isolate some of the areas where we can see that there is some concentration of strain or modal displacement that may warrant some kind of, or that may indicate some kind of damage. If we plot in a 2D format, So damage index versus height of the base, we see in some areas the damage index is very high. So that means this area may be overstressed because of the ground motion. Okay. And we can also calculate the strain energy contribution of each mode and see that these neck areas have higher strain energy corresponding to those modes. So that will also indicate some kind of either damage or high stress area. So this is a plot based on nonlinear analysis, material nonlinearity in the dam, where the TDSFEM is indicated by blue line and finite element results indicated by red line, which also shows quite good correspondence. So this is the crest displacement for the fixed base structure. And this is this is the horizontal displacement, and this is, I think it is mislabeled. One of them is horizontal, another is vertical displacement. So these are different conditions. If you see, this is fixed base. Fixed base means the dam is fixed at the bottom. Let me see if I can. Fixed at the bottom, and there is no reservoir effect or anything. It's just the dam structure. Okay. And this is the same thing. And then if we consider the dam with the effect of foundation, with the infinite elements at the edges, and the reservoir effect here, then we do nonlinear analysis. So the crest displacement looks something like this. Okay. Now this table shows the comparison of time in terms of one, two, three, four different cases. This is dam only. D means dam only. DR is with reservoir effect. DF means with the foundation. And DFR is the complete system, which is dam, foundation, and reservoir effect. Sorry, my handwriting on the screen is not that great. So nonlinear analysis of gravity dam. So let's complete this, the comparison of time. As you see, the time is consistently reduced in TDSFEM. So TDSFEM shows a great degree of computational efficiency. Now, one might ask that nowadays the computers are all improved. We have high CPU speed, etc. Why do we care about computational time? Okay, in any case, both are in seconds. It becomes useful when, say, you want to do uncertainty analysis of the system, where you want to analyze the dam or any kind of structural system for many different scenarios. And say in seismic analysis of dams, normally we analyze the dam for many different ground motion. okay, for earthquakes. And so if computational time is reduced by 40% in each analysis, and if we want to do 50 analysis, so it becomes so much easier if the computational time is lower. We don't have to wait for the analysis to complete before we start reviewing them. So again, the nonlinear analysis with the system then shows the damage in the neck area and the base area. Now, as I said, that for the AAR effect, we tried to find out the temperature distribution, and based on the temperature distribution, we applied extra temperature due to AAR. So this slide basically shows that suppose if there is this area of the dam is underwater, right? This is the reservoir site. And this is the downstream side. The tailwater is somewhere here, let's say. Most of the time it is ignored. And the foundation is below here, okay? So now this area doesn't get exposed to the sun that much because the water is here. But this area gets exposed to the sun on a regular basis. So in a hot climate, sometimes this surface can get heated up. And the temperature in this area would rise. Now, when concrete is cast and over the time it gets heated, heating accelerates the AR reaction. Okay. And this part of the concrete may go into the expansion mode. So based on the AR literature and the temperature distribution, we calculated what would be the expansion pattern in terms of the thermal stress, thermal strain. Okay, let's say this is the strain due to AR. We converted that to the thermal strain and then converted that to temperature. Okay, how do we do that? We first do a thermal analysis in the finite element or SFEM method, then find the temperature distribution. Then we apply the, there is a formula, not one formula, set of formula in the literature based on their research on AR as a function of temperature. So using one of the standard methods, we calculated EAR, epsilon AR, based on the temperature distribution. And then assuming that this is the temperature, that is the extra thermal stress in the thermal strain in this area. So then we back calculated the temperatures and applied that extra temperature here and do a thermomechanical analysis. So if we do that, then it has an impact in the analysis. We see that the distribution of stresses have changed. Here, the minimum principal stress. This is the maximum principal stress for static analysis. I think this is repeated. And this is the crest displacement. Okay, so if we overlay with, let me skip this and show you the AR effect only. So this one is the crest displacement considering the reservoir and the thermal effect, but no AR. Thermal effect means, if I go back to this slide, thermal effect due to ambient temperature rise. Okay. And then on top of that, if we apply the effect of epsilon AAR, then we get this. Now, it is not overlaid, but if we review the maximum displacement here, say this is around 0.16, maybe 17. And without AAR, it is much lower. So AAR can aggravate the displacement profile of the dam. Similarly, if we review the principal stresses, so this is no AAR condition. We see that the stress concentration in these two areas, which are the neck and the heel. So this is neck area and heel area. And this is the minimum principal stresses. Okay, now if we consider the AR effect, as I said, displacement profile changed, and you look at the distribution of maximum principal stress, the concentration of the stress changed. No, they are almost more distributed. Same thing with the minimum principal stress. So the AR effects is not always detrimental. Sometimes it could be beneficial, but most of the times it is detrimental. So because the stresses may be relieved a bit, but because of the displacement, higher displacement, it might affect other functionalities of dam, like the access tunnels or the gates. They might get squeezed and that will deform. So now from this study, what we can broadly conclude is that TD-SFEM takes lower time. Both modal and time history analysis shows that it gives comparable results with much lower computational time. And also it can be easily used for different kind of application area, like with dam with different levels of complexity in terms of dam only model, dam foundation, dam and reservoir, and dam foundation and reservoir kind of model. So, and linear, non-linear, all kind of scenario. It also we can also account for AR effect with some kind of modification that I explained. But there are a lot of things to do more, okay? One of the things is to integrate this analysis with the process of system identification and damage detection, uncertainty quantification, because even if we use material nonlinearity can be modeled in many different ways, okay? So, and also concrete is not a homogeneous material. So there could be a lot of inhomogeneity that we can model statistically, okay? So for that, we need a huge volume of analysis. And also we did only 2D. Okay, 2D spectral finite element methods. It could be adapted to 3D structures then, but those elements need to be developed. In case of reservoir modeling, we use the simplified Westergaard model, but as I said, we can use acoustic model, which is more meaningful, which we'll do in the next step. And crack propagation and all these things are not modeled here. That can be modeled in the future version of this work. Also, this was implemented as a research implementation as a prototype in MATLAB, but more robust development needs to be done. Also, we haven't considered geometric nonlinearity in our STFEM, TDS FEM. Geometric nonlinearity also need to be considered when we want to analyze slender structures. So I want to acknowledge this work. I'll start from the bottom. This work primarily is based on PhD thesis of my student who finished his PhD recently, Dr. Abhirup Sarkar. Now he is working with a big consulting company here. And I also acknowledge the funding sources from Natural Sciences and Engineering Research Council of Canada. And also I thank Central Water Commission in India and the Canadian Dam Association in terms of sharing knowledge, giving us information, sometimes good discussion. So with this, I want to thank you for your patience and interest in this topic. And if you have any questions, we'll be able to handle some of them now.
Vikas,
Thank you.
Vikas, please.
Yes, sir. Yes,
ask
sir.
questions.
Yes, sir. There are a few questions in the Q&A box.
Please.
I'm asking one by one. First, Mr. Varun Singh asks, a percentage difference in frequency of higher modes does not reduce monotonically with number of elements.
Yes, that is true sometimes because we compared like 1 to 1. 1 to 1 means if we have a 4-noded finite element, we compared with 4-noded spectral finite element. Okay. And as I said that since the integration profile is different, that creates some kind of difference. But usually spectral finite element needs to be used with higher order elements. So we haven't tested that because then it will not be the same comparison, right? So if we use, say, 10 elements, regular finite element versus 10 spectral finite element of regular pattern, then this difference will be there. But if we use spectral finite element with higher order, then this accuracy improves and the differences vanish. But we didn't want to do that comparison. But we wanted to stay 1-to-1 comparison. But you are right, there is some difference in accuracy.
Thank you, sir. Mr. Gaurav Vijay asks, how TDS FEM is done in which software?
Well, it is not available in any commercial software. That's why we had to do our own. So, because in commercial software like Abacus, SAP 2000, or any other software you pick, Adina, so they implement the regular finite element with material nonlinearity and all the things that we discussed. Okay, and their formulation is based on the way we learn finite element with Gauss quadrature integration, etc. We cannot alter because we don't have source code for this commercial software. So we had to develop everything on our own in that case, and compared with our analysis with commercial software.
Yeah, thank you, sir. Mr. Varun Singla asked, explanation for small differences between nonlinear time analysis results of FEM and TDS FEM. Why large difference in the initial time window? Would this reduce with increase in number of elements?
Yes, certainly. If you increase the number of elements, then these differences will vanish. But we also need to see that usually in the initial phase, there may be some differences, but the amplitude of displacement is lower. Okay. What is our more major concern in any kind of seismic analysis is what are the peak values. Okay. So if you consider the peak values, the differences are not high.
Okay, sir. Thank you. Mr. Rashid Latif asked three questions. First is, AAR behavior relates with the shrinkage cracks in which volume changes occur. Am I correct? Secondly, what is the remedy to cure AR after happening in a dam structure? As we know, generally it is called as a cancer in concrete. What are the lab tests to identify AR?
Yeah. So AR causes, as I said, it causes volumetric expansion most of the time. So that means some part of concrete may try to expand, but the other part of the concrete will not expand, so it will prevent that expansion. So some areas will be under compression, extra compression. Some area will be under extra tension. And concrete is very good in carrying the compressive force or compressive stress, but it's not very good at taking the tension. So that might create cracks in the concrete. Okay, that is one of the major problems. But it is more aggravated if you have an opening, if you have some kind of other structure in that mass concrete. So then it will try to push that other structure and break it. For example, if you look at a gate in a dam, and the concrete around it, if it expands, that it will try to squeeze that gate, and the gate will be damaged, okay, or not function properly. So that will be a major problem. So how to remedy that? So there have been attempts to really, they call it cutting the slots. So wherever there is some expansion, they will try to remove some concrete from there to create the zone of expansion so that concrete can freely move, and then seal it with some kind of sealant materials. Okay. In the lab test, they simulate in very different way, in many different ways. They have to first identify the reactive aggregates, and then try with different mix design with that reactive aggregates and measure the volume expansion. Okay. Those who are more inclined to look at the chemical nature of the process, they will study the chemical reactions within the aggregate and the cement concrete.
Yes, sir. Thank you, sir. Second question is, are the AAR and ASR similar?
They sound similar, but they are not similar. Because
Thank you, sir.
one is aggregate reacts with the concrete, right? Another is the silica. Silica means we are talking about finer aggregates.
Yes, sir. Thank you, sir.
And
The third,
AR is the coarse aggregates that we
coarse
use from the
aggregate.
field.
Yes, sir.
Yeah.
Yes, sir. Sir, his third question is, are the FRP and GFRP similar? Is it a perfect alternate of normal conventional deformed rebars in terms of strength, durability, and ductility? What are the pros and cons?
Okay, that will be a different lecture, but I will briefly uh, give the response here. The FRP is called fiber reinforced polymers. So in the field of aerospace or mechanical engineering, they are also called advanced composites. So advanced composites are widely used in aircraft structure and some other mechanical structure where you need to achieve lightweight and high strength. So in the civil engineering domain, about 2 decades ago, places like Europe, Japan, they started experimenting with this advanced composite for civil engineering structure in concrete. What is the motivation? Motivation is to reduce the risk of corrosion that happens with regular steel bars. Okay. So now FRP has many different versions. One is called CFRP, which is based on carbon fibers or graphite fibers. Then GFRP, which is based on glass fibers. Okay. And then there is basalt FRP, there are aramids. So GFRP is glass fiber reinforced polymer. Okay. So in all of these things together are called FRP. So what we do with FRP, application of FRP can happen in many different ways. One is called surface mounted strengthening operation. That means, suppose I have a beam. Let me draw a beam here. Just give me a second. So let's say we have a beam here, which is simply supported. And this beam is a part of a bridge deck. So it is supporting a bridge deck, let's say. And over the time, this area, the concrete cover spalled off, cracked, spalled off, and some of the rebars that were here, they got exposed and corroded, let's say. So that means the strength of this beam degraded. We need to retrofit. We need to strengthen it. So what we do is that we clean up this area, remove all the loose concrete, repair it as much as possible. Then we attach a FRP plate here, attached to it a strong glue with epoxy. Okay. And that takes extra tension and increases the capacity of this beam. That is called external application of FRP. But when you are constructing a new beam, instead of steel bar, we can use FRP bars, which are not deformed. We cannot deform it like our deformed steel bar. Instead, we construct some kind of ribs around this. So these are called ribbed rebars, FRP rebars. Now, in bond, it does not have as much good bond like the regular steel bar. That's why I need to design the bond length appropriately. But in terms of tension capacity, it sometimes is much higher than steel. Okay. So it has good tension capacity, but no ductility. Okay, that means if we have the stress-strain relationship of steel simplified this way, this will have a stress-strain relationship like this. That means it will fracture at this point without yielding. So this is strain and this is stress. So that means its fracture strength is many times higher than the steel bar, but it has no yielding. So that's why our code restricts its use in ductility sensitive applications. Okay. But we are using it for bridges, etc., keeping the design stress much lower, somewhere here or somewhere equivalent to the steel strength. Okay. So that we never reach the fracture strength. So this is the brief response.
Thank you, sir. Mr. Nagaraja asks, kindly explain how to decide number of elements to be used in the analysis.
So typically number of analysis is decided by, if you do any finite element analysis, you initially do some kind of sensitivity analysis or called convergence study. You take a coarse mesh, do the analysis, take a little bit finer mesh, and see how the results change. When the rate of change decreases substantially, that means your mesh is fine enough. You don't have to refine it any further. Because if you refine too much, it has a cost. Cost is in terms of computational time. And then those who do the analysis repeatedly, they develop some kind of intuition. And based on this intuition, sometimes you will find in finite element analysis manual or books, they will say, okay, you can say if you are analyzing a structure of certain length, you can have the mesh size of this, okay? That is, no element should be less than, say, 2% of the length, something like that. They might come up with some kind of guideline based on the intuition. But there is no, clear-cut rule that the mesh size has to be like this. It has to be done by trials.
Thank you, sir. Yeah, Mr. Prithviraj Bokeh asks, can we do TDS FEM on existing gravity dams for retrofitting and maintenance purpose?
Yeah, absolutely. We can do that. Yeah. So as long as you can model a structure with regular finite element method, you can do with this.
Any more questions?
Yes, sir. This is there is one more last question. Mr.
Please.
Gaurav Vijay asks, have the analytical results been compared with realistic correlation derived from actual dam performance as obtained through a structural health monitoring system? If not, please suggest a suitable SHM instrumentation and monitoring scheme may be proposed to enable proper validation and long-term performance assessment of the dam.
Well, again, this is a separate lecture. There can be a whole lecture on this. So again, briefly speaking, that yes, there are existing dams with some instrumentation. We tried to gather some instrumentation data to validate our analysis. Sometimes we take benchmark problems for that particular purpose. But many a times the dam authorities do not want to share their instrumentation data that freely, okay? But there is instrumentation, but main problem with the SHM of dams and instrumentation is that many dam owners will be excited about instrumentation. They will do the instrumentation, collect data, but then there is not much of follow-up. There's not much of analysis of the data to assess the damage, assess the health condition on a regular basis. This is what we are trying to encourage. And in course of time, I'm sure we'll have more data and more correlation studies.
Yeah, thank you very much, sir. These are the questions.
Excellent presentation, Professor. My small query before I conclude. You have taken only 3 modes. I mean, with the 3 modes are enough, or we have to take more? And if more modes, in which circumstance?
Yeah. Typically, we choose the number of modes because based on their mass participation. So if here 3 modes are taken just for example, but in real analysis, we'll have to extract as many modes necessary to achieve high level of mass participation, at least more than 90%. So that is the common practice in seismic analysis.
Professor, I mean, excellent presentation, and I am sure people listening this webinar will definitely have, some extra information and which we can use in their personal structural analysis and design. And thank you on my behalf and on behalf of Institution of Structural Engineers India for you to spare valuable time, that too from such a far off place, and sharing your knowledge and experience for the benefit of our young budding sector engineers. Thank you once again. And
Thank you very much. I'm glad that I could present in front of all of you, and I hope you got something from here. And if there is any follow-up question or anything, please forward it to me. I'll try to respond to you as necessary.
right. Thank you so much. With that, let's conclude the session.
Yeah, thank you. And I just want to talk about the maple leaf here. You might be familiar with it. This is symbol, Canada's national symbol, because we have a lot of maple trees around us. So
Right.
thank you very much. And thank you from Canada and from Concordia University. And I invite all of you, if you have any chance, any time in the future, please visit us here.
And thank you again for sharing and your knowledge and experience to our young
right.
sector engineers. And with that,
Thank
let's
you.
conclude.
Thank you. I'll unshare this screen.
Thank you very much, sir.
Okay. So I can sign off now?
Yes, sir. We are closing now. Yes.
Okay.
Right.
Thank you very much.
Thank you.
Take care.
Okay.
Bye.
Have a good
Bye.
day. Have a
You
good day.
too.
Bye-bye.
Bye.